in that drawer that says it's not by the two toolbox. And it says like, well, something, there's bags. I don't know if they're the right ones, but there's bags straight up for like a whole torch bar. What's that?
It's like the maker, completely.
Oh, the torch.
Yeah,
Yeah, because those are like a flex step. Like,
and it's always been like broken, but like I was trying to use it today, and I was like, dude, like, because I grabbed it, and it's like, freaking dangling around. I'm like,
oh, okay.
yeah,
So looking.
Brandon knows how to like switch that out, right?
I mean, I think you should be able to figure out because in the baggies in that drawer are like the whole torch, like the whole handle part.
But then like the inside portion too is like snapped.
Oh, like maybe something on the hose side broke, so that goes into that.
Yeah, like
If we're lucky, maybe it broke on the torch side, and we can take the hose part out and put it into the
exactly. Because it's like that. I think it's that hose part, and then that's part of the torch. So it literally looks like somebody like grabbed like a knife open and started like cutting away.
Well, yeah, how's that?
I have no idea.
I'll look at it. If you guys haven't figured it out by the time I get out of class, I'll look at it.
Yeah, because I know you guys were like looking at it the other time. I'm like, oh, look, it looks like it's broken already. Or something is loose. And then today I was like looking at it, grabbed it, and started dangling on its own.
Yeah, I'll take a look at that drawer.
All right.
Because it might just be a rip it out and push it.
All right. All right. Cool. Now I gotta do that. It's such a whole thing that's. Place that.
Hey, Jacob. A little bit better. Still hurts though. Not really. He kind of wanted to get rid of me because he was like 40 minutes late for my appointment, and then I could tell he was trying to use me to get back on schedule. So yeah, he was just trying to talk to me quick. But he says it's probably muscular, and so he said just ice and take ibuprofen, and you know, he said if it doesn't get better in 3 weeks again, then just let him know and then I could come back. But yeah,
it's literally like the meme. Ice and ibuprofen. Okay, that'll be $10,000.
yeah.
Those are the worst kinds of doctors.
Yeah. I was like his second patient of the day too. I'm like, why was he talking to the first patient for like that long? Yeah. It was well, I mean, I guess it is what it is. The nurse took my blood pressure, and I don't know if I was just getting upset or if I was nervous, but I had a really high blood pressure. But anyway, I also know that I don't take care of my body the way it should. So it's good motivation. Now I have the numbers of, you know, how much more I need to improve my blood pressure. So
They only took it once?
yeah, they only took it once.
That's weird because they usually, well, at least for when I go to my checkups, they usually check it twice if it's high.
Yeah, the nurse said, yeah, maybe I'll come back in like 10 minutes if you're not feeling nervous, but she never came back. And so they just left me in the room for like 40 minutes.
Yeah, it could be what they call white coat syndrome too,
What's that?
where you get like a little bit, you get elevated blood pressure reading from the doctor's office.
Yeah. I'm sure it is. Yeah.
Okay, I'll be back.
Yep. Mhm. I see. Yeah, so far I just usually just when I go to or when I get home, I just lay on my bed and I put an ice pack under my butt, and that seems to help. Usually if I go and walk around for a bit, then it helps a lot too. It usually only hurts really when I sit for a long time and I get up. And so like right now it's a bit sore because I was sitting in my office for a while, but yeah, usually if I walk around a bit, it feels better.
They tried stretching it out.
Yeah, I try to do stretches too.
Yeah, I
It's,
remember.
it's definitely getting better. It's definitely not getting worse, and so that's a good thing.
Yeah, that's good. I remember I pulled my back out when I used to deadlift, so I had to like do all sorts of stretching and deep squats just to stretch that lumbar region properly.
Oh yeah, I think you told me about that. You know, like last year or something.
Yeah.
Hey guys. Yeah, the back is so like if your back's hurting, it really just affects every part of your body.
It really does.
You don't realize how much you rely on your back. Okay, it's 5:30, so let's go and get started. All right, good evening, everyone. Happy late Easter if you celebrate that. How's everyone doing today? Good. Week 13. So yeah, we're getting there. So we have 4 more weeks of instruction, and then we have finals week after that. So very close to the end. Okay. So announcements. Remember our midterm is on Monday. Okay. I came in here and I heard Dr. Wang talking about his midterm. Like, oh yeah, that's probably why the midterm, our midterms on Monday, because yeah, you guys would go back to back with mine. So yeah, so our midterm is going to be on Monday. Okay. Oh, I forgot. So I already filmed the review video, so I did that on Friday. Did I didn't send it out. I didn't send it out yet, right?
No.
Okay, yeah. So I need to do that. So I'll send out the link. It's on YouTube already. I just didn't get a chance to send it out yet. So you guys have the study guide. You guys have the midterm review video. I do have one more homework for you guys. That's kind of concerning the stuff we're going to cover, probably starting today and Wednesday. But I'll wait till after the midterm to assign that, just so you guys only have one thing at a time. Okay, and so the plan for today is we have a little bit left on the lecture notes for convection finite volumes. And then after that, we're going to move on to a set of lecture notes on higher order schemes, okay? So higher order schemes, if you've been working on the project, you've been looking at it, higher order schemes is part of the final project. And so after we cover higher order schemes, you should have everything you need to do the final project with finite differences. If you're a grad student or if you want to do with finite volumes, we still have a bit more to cover. And so you're gonna have to sit tight just for a bit longer. But after this week, you should have everything you need to do for the final project if you're gonna use finite differences. Okay. Okay, and so that's it for my announcements, and so not too much today. And so, are there any questions I can answer before we get started? Okay, all right. So let's go ahead and pick up where we left off. We were talking about convection with finite volumes. Okay, specifically, we're working on 2D, and so I think we were just at the precipice of an example. Okay, and so the idea with 2D finite volumes, and so just as a refresher, and so our 2D finite volumes are going to take place on these square cells. Okay, and remember the way that this works in 2D is that we basically split up our cells into each of the different edges. Okay, so we have the north edge, we have the east edge, we have the south edge and the west edge, okay? And we have all their corresponding normal vectors. Okay. And then what we do mathematically is that we evaluate each of the integrals on we evaluate our finite volume integral on each of these edges. Okay? Okay. And so of course here, we have 4 edges, and so that means we're gonna have 4 integrals, okay? And so everything that we're gonna be doing is gonna be based on those 4 integrals. And so when we include convection, our integral looks like the following. And so we have an integral like this. Okay? Of course, this is a line integral. And so when I say we're gonna evaluate the integral, we're integrating along a single edge, just like this, okay? And so it's line integral going from that. And so the integrand is we take our solution value phi, we take the dot product between the velocity vector and the outward unit normal. Then we subtract the diffusive term. And so that's gonna be minus k, which is our diffusion coefficient, multiplied by gradient of phi, dot product with the n normal vector, ds, okay? Right, and then we apply this integral on each of the sides. Okay? And so normally what we do is if we have an interior cell, we plug in expressions for these, based on a linear approximation. Okay? Okay. And so for the diffusion term, what we usually do is we take the average, okay? And so we take the average of phi sub c plus the neighboring cell. Okay. And we divide by 2. And we multiply by the corresponding component of velocity, right? And so in here we have like an x velocity, okay? Right, so that's the contribution from the convection term. And then for the diffusion term, we have k, and then we have our derivative. Okay, and so our derivative we approximate with a linear line. Okay, and so we compute that slope, right? And so the exact expression of this is going to vary depending on which side of the square that you're on. Okay, and so let's say if we do this on the east side. On the east side, we just use a simple kind of forward differences. So we have phi sub neighbor on the right, okay, minus phi sub c divided by delta x, okay? And all of this is multiplied by the length of that edge, okay, due to the trapezoidal rule. So this delta y right here is the length of edge we are integrating on. Right? And so that's an example of how we would evaluate one of these integrals. Okay, so I try to leave it vague, but kind of in this form, we assume it's on the east side. Okay, and so we would then repeat this for all 4 edges. Okay. Okay. After we repeat it for all 4 edges, we have 4 integrals. Then we simply just add the results together. Okay. And then by that point, once we add all 4 of those together, we get a single algebraic expression, okay, that we can use to form, our linear system. Okay? So that's the most general case. So that's the interior cell. And I think what we just finished talking about last time was how to handle boundary conditions. Okay? And remember, with finite volumes, the way we approach boundary conditions is different. And so what we do is we take our standard form for our interior cell and then make adjustments based on the boundary conditions. Okay. I believe that was kind of the last thing we went over last time. And so, depending on if you're a Dirichlet boundary condition or a Neumann boundary condition, you're going to make the different adjustments. Okay. And so Dirichlet, we've done, quite a few times already. And so the one I wanted to quickly review was the Neumann boundary condition.
Excuse me.
Yep.
Real quick, that the equation up above, though, that's for without the whole taking into consideration the direction.
Yeah, so the direction is kind of already kind of baked into it. So even though I try to keep it vague with neighbor, of course, it depends on, the direction of the normal vector. And so, with this one, I kind of implicitly assumed that the normal vector was 1, 0. But then, yeah, you would make adjustments for the sign depending on if the normal vector was -1, 0, or 0, 1, or -1, 0, stuff like that. Yeah. Mm-hmm. Okay. And so Neumann boundary conditions are pretty easy. And so we're basically just going to replace the entire integral. Okay. And we'll do an example of that just in a second, just so that you can see. Okay, so that's kind of just the overview, and so that's how we generally tackle convection problems in 2D with finite volumes. And so next we're going to do an example, and we're going to follow the same kind of logic, and so we're going to work it out by hand first, and then we'll jump into the code where we'll see those hand calculations illustrated in code there. Okay. But are there any questions on this before we jump into that example? Okay. All right. So let's go ahead and jump in. And so let's say that we have the following example. And so we have 50 partial phi partial x plus 5 partial phi partial y is equal to 2 partial squared phi partial x squared plus partial squared phi partial y squared plus 3xy. Okay. And so here we have full, convection, diffusion, and a source term. And so we're going to solve this equation on the following grid. So we have a two-dimensional grid because we have a 2D problem. Okay. And we're going to have 16 cells. And so we're going to have 1, 2, 3. And so this will be cell 1, cell 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Okay. And so the boundary conditions on the right side here, we're going to have a Dirichlet boundary condition of 25. On the left side, we have a Dirichlet boundary condition of 50. Up top, we have another Dirichlet boundary condition of 50. And on the bottom, we're going to have a flux value. Okay, so that's our Neumann boundary condition. And we're going to have a Neumann boundary condition of 0. Okay. Okay. And so for this problem, what we are interested in doing is we want to solve this problem using finite volumes. And so that means we're going to write out the finite volume equations by hand. Okay. All right, and I guess before we start plugging in, let's go ahead and write out all the parameters. And so first we're going to write out the value for the x velocity u. And so from this problem here, we can see that that's equal to 50. Okay. Then we have the y velocity v. This is equal to 5. K is equal to 2. Okay. And we're going to assume that our domain here has lengths of 1 in each direction. Okay, so we have Lx is equal to 1, Ly is equal to 1. Okay. All right, so the way we're going to proceed with this is that we're going to do a couple examples of interior cells, and so we might do cell number 6 or 10 or something like that. Okay, so that's just a straight up plug and chug, and then we'll do some of the boundary cells just so you can see, you know, how those adjustments are made. Okay, any questions on the setup for the problem? Okay, so let's go ahead and start. So let's start with the interior cell. Let me just do one because they're all basically more or less the same. Okay, so we're going to plug into our interior cell expression. And so if you look back in your notes a little bit, then you can see for interior cell, our finite volume equation is U multiplied by the grid spacing divided by 2 minus K P sub E plus minus V delta divided by 2 minus K V sub south plus minus U delta divided by 2 minus K V sub W, okay, the west neighbor. Then we have a plus V delta divided by 2 minus K V sub north neighbor, plus 4K phi sub C is equal to Q of XC YC times delta squared. Okay. And so we're just going to plug straight into this equation here. Okay. So let's do cell number 7 because that one's a little bit interesting. Okay. And so if we plug in the numbers for this, what we get is 4.25 for this first term, okay, multiplied by its east neighbor. And so the east neighbor for 7 is going to be phi 8. Then we have a minus 2.25 phi south. And so the south neighbor for cell 7 is phi 3. Okay. Then we have minus 4.5 times phi west. And so the west neighbor for 7 is phi 6. Okay. Then we have a minus 1.75 times the north neighbor. And so the north neighbor is phi 11. And then we have a 4K times phi sub C. And so K here is 2. And so 4K is going to be 8. Okay. And phi sub C, of course, is 7. All right. And then we multiply our source term. And so our source term is 3 XC YC, right? Because that's our source term from the problem, 3XY. And then we're going to multiply that by delta squared. Okay. All right, so that's our first algebraic equation. So it's just kind of a plug in and chug. Okay. We could take this one step further because we can go ahead and plug in for the right. Okay. Remember X sub C and Y sub C, these are the XY coordinates of the cell in question. Okay. And so you know, just based on this problem, if we know that the lengths of each side of the domain is 1, and we know that we have 4 cells in each direction, what this tells us is that the grid spacing delta is going to be 0.25, or in other words, it's going to be 1/4. Okay. Okay, so let's apply that in order to compute its X and Y centered locations. Okay. So let's do the X component first. And so we know that each cell here, the length of that is going to be 0.25. Okay. And so cell 7 is located just above cell 3. So first we're going to add the first two blocks right here. Okay. And so the first two blocks, right, we cross over two cells, and so that's going to be, this whole length right here is going to be 0.5, okay, just to cross over cells 1 and 2. And then to get to the center of cell 3, we're going to pass over a half cell length, okay? And so this is going to be plus 0.25 divided by 2, okay? And so you add that all together, we get 0.625. Okay, so XC, 0.625. Okay. And then if you use that same logic for Y sub C for cell 7, Y sub C here is going to be 0.375. Okay. Meanwhile, delta, we know delta is 0.25. Okay. And so to evaluate that source term, we take 3 times the x coordinate, which is 0.625, times the y coordinate, 0.375, multiply by 0.25, 0.25. Okay. And so I don't have that number off the top of my head, but you know, it's just kind of plugging in from there. Okay. All right, so that's the interior cell. And so, you know, interior cells are always straightforward. And so, you know, whether you're doing code or whether you're doing it by hand, you know, I always recommend that you start with the interior cells. So that's kind of, you know, no real ambiguity there. And so, you know, start with that, get some momentum, then you start to get a sense for what the problem is like. Okay. Then after you do the interior cells, then you can start working on some of the boundary conditions. Okay, and so with that, let's do a boundary condition on the south face. Okay. And so cell number 3 here is as good as any. Okay. And so cell 3 looks like this. Okay. Where on the bottom, we have a Neumann boundary condition of flux is equal to 0. Okay. But on every other side, we have neighbors. Okay. All right, so what this tells us is that, you know, because we're boarding one boundary condition, that means we're going to modify the south integral to account for that boundary condition. Okay. Okay. And so let's go ahead and do that. And so our south integral here, so we have integral over the south edge of phi v dot n hat minus k gradient of phi dot n hat ds. Okay. Remember, with Neumann boundary conditions, we're going to replace this entire integral. Okay. And so this entire thing right here, we're just going to replace it with gamma. Okay. And so we end up with gamma integral ds. Okay. And so this integral ds is going to be the length of that edge. Okay. And so the length of that edge is just going to be the length of a single cell. And so that's going to be delta x. Okay. And so we end up with gamma delta x for that integral. Okay. Okay, so that's the modification that we make for this cell. But all the other integrals, the north integral, the west integral, the east integral, all of those are going to stay the same because, you know, we have neighbors on that side. And so keeping in mind that all the other integrals stay the same, we can just write their standard expressions and then just add up all the contributions.
First, I had a quick question.
Yep, what's up?
That's the integral south, right?
Yes,
That's
south. Yeah, it's a little scuffed. Let me write that again. Okay. All right, any other questions on what we did here before we write out the expression? Okay, all right, so I'll do this one fully, just so you can see all the terms, just so you can see how it is. But you can, from here, you can kind of take shortcuts because it is quite a lot of writing to do. Okay, so let's do the east integral first. And so the east integral, after you evaluate the integral and everything, you end up with the following. Let me color code this. And so this will be the east integral. And so the east integral is u delta divided by 2 times phi sub c plus phi sub e minus k, k over delta, or excuse me, just k, I'm sorry, because we already multiplied by delta, minus k, phi sub e minus phi sub c. And so this entire expression here is the east integral. Okay. Then if you proceed clockwise around the cell, next would be the south integral, but we're already replacing it. And so the south integral, since we have a boundary condition, is just going to be gamma times delta x. Okay. Sorry, it should be a minus delta because it's the south face. Okay. Because remember, the south normal vector is 0, comma, -1. And so when you take the dot product, you end up with a minus right there. Okay. Right, next, we have the west integral, which is going to stay the same. And so we have a minus u delta divided by 2 phi sub c plus phi sub w plus k phi sub c minus phi sub w. Okay, so this right here is the west integral. Okay, and then finally we have the north one. So the north integral is going to be plus phi delta divided by 2 times phi sub n plus phi sub c minus k phi sub n minus phi sub c. Okay, so this here is north integral. Okay, so here we have our 4 integrals together, together with the one that we modified, and so we modified the south integral one. Okay. At this point, we can go ahead and plug in the value for gamma. And so in this case, it's easy because we have a gamma of 0, right? Okay. And so for this problem, the Neumann boundary condition is actually 0. And so that whole term is just going to cancel out. Okay. And so if you add those together, then you end up with the following. And so you add these together, you get u delta divided by 2 minus k times phi sub e plus minus u delta divided by 2 minus k phi sub w, okay, plus v delta divided by 2 minus k phi sub north, okay, plus 3k phi sub c is equal to 3xcyc delta squared. Okay. Notice how all the terms here, so the east term, the west term, and the north term, all of them are exactly the same as before, right? So if you compare it to our generic expression for the interior cells, this term, and this term, all exactly the same. The only thing that changes is just the south one. Okay? And in this case, it's just totally gone because we have a flux of 0. And so from here, you would plug in numbers and you would get algebraic expressions. So this would work for cells 2 and 3 because those two they have identical conditions, right? And so they both have a Neumann boundary condition on a south border. Okay, any questions on this? Okay, all right, so let's do an example with the Dirichlet boundary condition, the harder one. And so let's do cell number 5. Okay. And so cell 5 has a Dirichlet boundary condition on its west side. And so since the Dirichlet boundary condition is on the west edge, that means the integral that we're going to modify is the west integral. Okay. And so we have integral on the west of phi v dot n hat minus k gradient of phi dot n hat ds. Okay, and we're going to modify this according to the boundary condition. So let's say that the boundary condition is phi o. Okay. Okay, so that's going to be our specified solution value there. And so if we plug in for this, we get a minus phi naught u delta. Okay. And so the minus sign is appearing because of the normal vector, right? Because for the west integral, the normal vector is -1, 0. Then we have a plus k delta times the slope of the line between phi sub c and the value. Okay, so we have phi sub c minus phi 0 all divided by delta divided by 2. Remember, we have delta divided by 2 because we only travel a half distance between the cell center and the cell edge. Okay. Okay, so let's go ahead and simplify this. And so we simplify, what we get is minus phi naught times u times delta plus 2k phi sub c minus 2k phi sub naught. Okay. And then, of course, everything with phi sub naught, we move to the right-hand side of the equation because they're known quantities now. Okay. And so we can proceed from there. Okay. And just like the Neumann boundary condition above, every integral that's not west, and so the north integral, the east integral, and the south integral, all of those are going to stay the same. Okay, so let's go ahead and do that. And so I'm not going to write out all the integrals again because it's basically the same as up there. Okay, but if you plug in everything, you end up with the following. So you end up with u delta divided by 2 minus k phi sub e plus minus v delta divided by 2 minus k phi sub s, okay, plus v delta divided by 2 minus k phi sub n. Okay. Again, notice how all of these are the same as usual. Okay, so these are our normal interior cell coefficients, which makes sense because we have neighbors on those sides. And then we start with the differences, and so we have a plus. Normally we have a plus 4k, but now we have plus 5k. Okay. 5k phi sub c. Okay. And so we get an extra contribution to phi sub c due to the Dirichlet boundary condition. Okay. And this is equal to 3xc yc delta squared. Right. So we have our source term. And then we have our extra contributions due to the Dirichlet boundary. So those are the two terms that I circled above. And so we have a phi naught u delta plus 2k phi naught. And so that's an example of how you would handle a situation when you have, when you have a Dirichlet boundary condition. Okay. All right, I'm going to do one more example with the corner cell, just so you can see it, and then we'll see how it's implemented in Matlab. Okay. But are there any questions on the Dirichlet boundary condition here? Okay. All right, so let's do a corner cell. Okay, so let's do cell 1. And so cell 1 has two boundary conditions. Okay. And so first we have a Dirichlet boundary condition on the west edge. Okay. And we also have a Neumann boundary condition on the south edge. Okay. And so that means the north integral and the east integral are going to stay the same. Okay. And so if we go ahead and skip ahead, right? And so I picked this one on purpose because we basically just did both of these. And so we apply basically what we did, but twice on the same equation, we end up with the following. Okay. All right, and so we have our phi north term, and so phi north is v delta divided by 2 minus k phi sub north. Remember, this one's unchanged because we have a neighbor on that side. Then we have the east contribution. Okay, so the east contribution is u delta divided by 2 minus k. Okay. Then we have our contributions from the Neumann boundary condition on the south and the Dirichlet boundary condition on the west. Okay. And so from the south, we already know, based on up here, that the south one is just going to go away because we have a flux boundary condition of 0. Okay. And so we have nothing from the south. Okay. And then from the west, we have the contribution that we just saw up here. Okay. And so remember the convention that we have for Dirichlet and Neumann. Okay? And so the only term that I haven't written yet is the phi sub c. Okay. And so remember, for Neumann boundary conditions, we subtract one from the or we reduce the magnitude of the phi sub c, because normally it's 4k, right? So that's what it is in the default case. And so we know for a Neumann boundary condition, instead of 4k, it becomes 3k phi sub c, right, as we see up here. Okay. And so this is due to Neumann. Okay. But we also have a Dirichlet in this case, and so Dirichlet will add to the magnitude of phi sub c, right? And so if we look at the solution for just the Dirichlet boundary condition, we end up with a 5k instead of a 4k. Okay, and so we're once again going to increase this by 1, and so in the end we actually end up with 4k phi sub c. Okay, and then on the right hand side we have our source terms. So we have 3xc yc plus our extra contributions from the Dirichlet boundary conditions. We have phi naught u delta plus 2k phi naught. Okay. Okay. And so that's the kind of thought process that you should run through when you're doing these kinds of problems. Okay? And so, if you first of all start with the interior cells, okay, list out kind of the general expression, then go ahead and move on to the boundary conditions. And when you do the boundary conditions, you're just going to modify or replace, the integrals that are on the boundary. Okay, everything else you're going to leave the same. All right. Any questions on this before we hop into MATLAB? Okay. Question. So this could be used for the project? Yeah. A bunch of code that we've written throughout the class can be used for the project. Yeah. The project code is not revolutionary. It's not a brand new code. And so, I would say probably, at this point, probably like 80% of the code that we've, the final project code is probably 80% comprised of code that we've already written. And so, it's just kind of putting things in the right places and just kind of making sure that you understand it all. Yeah, that was kind of my approach with the final project. It's not a revolutionary problem. It's not something that's totally out of left field, but it is a good application of everything that we've learned. And so, part of the project is, taking parts of the class, taking parts of the codes we've gone over together and just putting them in the right place for the final project. Yeah, I take a little bit of the training wheels off for the final project. That's the main thing. Okay, all right, so let's go ahead and switch over to MATLAB. Okay, that's not the code. This is the code that I want to see, although this is way too big. So let me go to Home, Preference, and Font. Okay, 18 is a lot better. Okay, and so here is our first 2D convection diffusion, this is the one we want, sorry. So this is our first 2D convection diffusion code with finite volumes. Okay? And so the thought process behind this code is very similar to our 2D diffusion. I know that was kind of giving people some fits for a while, but I think in some ways you'll find this code is actually easier to deal with because, if you remember from our 2D diffusion code and for finite volumes, we kind of tackled two integrals together at the same time. So we did the east-west integrals at the same time, and then the north-south integrals at the same time. Right. And I think that part was kind of tripping people up a little bit. But what you'll see in this code is that we actually have separate if statements for for each of the four integrals. And so inside that for loop, you'll have, basically four different if statements that correspond to the four different integrals. Okay. Okay, so first some basic stuff out of the way. And so here we're defining all of our variables. And so we have the length of the domain, the number of cells, all the parameter values, and so on and so forth. Okay. And so I'm not going to spend too much time talking about that, but let's go ahead and jump into the meat of the code, which is our for loop, okay? And so just like all our other codes, we have a for loop here that's going to populate our left-hand side matrix and right-hand side vector, okay, based on the four integrals. Okay, so first thing you see is that we have to compute our ID numbers, and so these are the specific rows in our left-hand side matrix that corresponds to phi sub c, phi sub w, phi sub e, phi sub north, phi sub south. Okay, and then what you see here is that I have separate if statements here, okay, corresponding to each of the integrals. All right, so let's go through one of them slowly. So let's go through the east integral first. Okay, and so remember the east integral. Let me see if I can write this. So the east integral is integral of phi v dot n hat minus k gradient of phi dot n hat ds. Okay, a little jank, but I think you can read it, right? Okay, and then when we evaluate this term becomes phi sub c plus phi sub e divided by 2 times u. Okay, and there's also a delta. And we have minus k phi sub e minus phi sub c divided by delta multiplied by another delta. Okay. Okay, so what I just wrote here, or attempted to write, this is what our formula is for an interior cell, right? Because in order for us to evaluate these expressions, we have to have an east neighbor, right? So that's what phi sub e represents. And so remember what I said, when you're kind of working through the logic of these codes, do the interior cell first, okay? And so if you look at the structure of this if statement, and so first thing we're going to check to see if I is equal to nx, okay? And so if I is equal to nx, where nx is the number of cells in the x direction, that means we're on the complete right side of the domain, okay? And so in this case, we apply our Dirichlet boundary condition. And so we're not going to worry about this first part just yet, okay? But we'll come back to it in just a second. But let me work on these parts, okay? And so these are our contributions to the left-hand side matrix if we have an east neighbor, or in other words, if we're interior, if our east face faces another cell, okay. And so you can see for a Maya d, I add a u delta divided by 2 plus k. Okay, so this is for, or I guess I wrote it already. So this is a coefficient for phi sub c. Okay. And so if you work through the math for this, and so if you look for all the coefficients for phi sub c, you can see here that we have a u delta divided by 2, okay? And you can also see that we have a positive k, right? Because we have a deltas cancel out, and we have a minus is going to cancel out, and so we have a positive k for that one, right? And so these two terms right here, represent exactly those contributions to the left-hand side matrix. All right, and then you can see the exact same thing for phi sub e as well. So for phi sub e, we have the the convective contribution, which is u delta divided by 2, okay? And then we have a minus k. And so we have a minus k times phi sub e divided by delta, multiplied by delta. Deltas cancel out. And so that's why you just have a minus k right there, okay? And so the way this code is structured is that it takes each integral individually. And so, actually this makes the boundary conditions, really nice, because if you have a corner cell, this automatically checks for it because it's checking each of the sides of the cells, just naturally. And if it is a boundary condition, then it makes the modifications for the code right away. Okay. And so this is nice. And then at the end, it basically adds all of these up together, or it adds all of them up together as it's constructing it. Okay, so that's the logic for this first integral right here. Okay, so we're going to repeat the same logic for the south integral, the west integral, and the north integral as well. But does that make sense about how we structure this part of the code right here? Okay. Right. So I think this is a little bit cleaner than our 2D diffusion, because 2D diffusion was a little bit messy because we did x and y, or east and west together, north and south. This is just, we'll just tackle one integral at a time. Yeah.
Could we have done the same thing on that one? Just break it up into.
You could. Yeah. Yeah. And it's one thing I kind of wish I did, but at the same time, I think kind of seeing both ways, I think gives you kind of a fuller understanding of both. Yeah. But absolutely, you can definitely do 2D diffusion like this as well. It would definitely clean up the code a bit, or make it easier to read. Mm-hmm. Okay, all right. So let's do the boundary condition now. Okay, and so if we have a boundary condition, let me go ahead and erase this. Okay, and so for the west face, okay, for the east edge, we have a Dirichlet boundary condition of 25. Okay. And so if we do that, then this term right here, this phi v dot n, and so this is going to turn into 25, because that's the Dirichlet boundary condition, multiplied by u. And we have a delta. We have a delta that comes out just based on the integral here. Okay. And then this term, if we put it out, is going to be minus k times phi w, or phi naught, excuse me, minus phi sub c divided by delta divided by 2 multiplied by delta. Okay. And then just like before, any term that you see with phi sub naught, we're going to move that over to the other side of the equation. Okay. All right, so let me simplify this a bit just so you can kind of see it. And so we have a 25 u delta, okay, minus, and I'll go ahead and plug in for this at phi naught as well. And so we have a minus k, minus 25k, or 25 times 2k, excuse me. Right? Because we have a 2 that comes from the denominator and we have a k that comes out in front. And then we have a plus. We just have a regular plus 2k phi sub c. Okay. So does everyone see how I got these expressions here from the equation above? Okay. All right, and so let's go ahead and see how that applies. Okay, that should be u right here. Okay, and so first let's do the left-hand side contribution. And so we have only one phi term here. And so we have a phi term, phi sub c is going to be a plus 2k, right? And so if you look at line 34 in the code, you can see here that we have a my plus 2k, okay? And that represents the coefficient for phi sub c only for this integral for a Dirichlet boundary condition, okay? And then of course, we don't have, because we're on the boundary condition, we don't have any contributions to east ID, okay? And so that's missing. But instead, what we have a contribution to is the right-hand side forcing vector. Okay, so here we have b my ID. And so make sure you kind of pay attention to that kind of subtle difference. And then to b my ID, we're going to add these terms right here. So first we have a 25 times u times delta. And we put a -1 here because we're moving these over to the other side of the equation. So this becomes a minus, this becomes a plus, right? After we move it to the other side. And then we also have a 25 times 2k. And so that's what this term is right here. Okay. Okay. And so now that we have the interior cell contribution and now that we have the boundary condition contribution, our east integral is complete. Okay. All right, question, could I have also written 2k minus u dy? Yeah, you could. Yeah, that might actually look a bit cleaner. Yeah, so because it's all algebra, and so it doesn't really matter what order that you put it in. I think the reason I did this was because I was going off the same order for this one. Yeah, but you could definitely do 2k minus u dy, and you get the same thing. Okay, so that's our east integral, and so I want to do that one slowly, just so that you kind of see the logic of how I constructed this code right here.
One more time.
Yeah.
So it's positive. So the first term is positive when we first write it, and the second term is negative. But when we move it over, it becomes negative.
Exactly. Right. Yeah, because at first, this is a positive right here, and this right here is a negative.
And that's just because it's on the east edge. Right?
Exactly, yeah. So the signs for this side are mostly determined by the n hat here. And so whatever the normal vector is for that edge. And so since this is an east edge, you end up with the positive here and a negative here. But then when you move it to the other side of the equation to be in the b vector, then their signs swap because you kind of subtract one from both. You subtract it from both sides, basically.
Everything.
Yep. All right, any other questions on this? Okay. All right, so let me go ahead and clear this. Okay, so that's the logic for the east integral. I'm not going to go over the logic for the southwest and north that delicately, just because that kind of took a lot of time. But you can go through that exact same exercise. Okay. The only thing I would caution you a bit is just pay attention to the signs. Okay. And so in particular, let's compare the signs for the interior cells for the east versus the south. Okay. And so let's look at for an interior cell on the east, we get a positive u dy divided by 2 and a positive k for phi sub c. Okay. But for the south integral, instead of a positive convection velocity, we end up with a negative one, right? Because again of the normal vector. But we still get a positive K because, the normal vector is there, but it cancels out with the other sign, and it cancels out with how we define the slope for the diffusion as well. Okay, and so just kind of pay attention to the sign as you're going through this code. Okay, because it's subtle and it can really it can really kind of confuse you if you're not kind of carefully looking at the signs. Same thing for the south neighboring. So instead of a positive convection velocity, we have a negative. Okay, so just kind of pay attention to that as you go along. Right? Okay, so that's the south integral, and so the south one is actually the simplest because we have a zero flux there. Okay? And we do the same thing for the west and the north. Right, and then we add our source term or forcing function. That's more or less the same, and then and that's about it. And so let me go ahead and run this. Okay. Maybe I shouldn't have done a 75 by 75, but it looks so nice when it's so high res. Okay, and you end up with the following solution. Okay, so this is pretty high res because I did 75 by 75, but if you use less cells, then it's not going to look this fine. Okay, it's also going to run a bit faster. Okay, and so the upshot with these kinds of codes, and feel free to do this with your 2D diffusion code as well, is that we're kind of meticulously evaluating each integral one at a time, in the code. Right? And so hopefully that should make things a bit easier to do with finite volumes. And you could take the same approach with your project as well. And so the finite volumes for the final project actually is I'd say they're both about equal difficulty, both finite difference and finite volume. Okay. All right. Any final questions on this before we move on? Okay. All right. And so that's it for convection with finite volumes, right? And so we are done with that. Let me bring back my iPad. Okay, and so now we're ready to tackle the next topic, okay, which is a big part of your final project, which is higher order convection schemes. Bless you. Okay. All right, so this is actually a good segue from what we just did, because because we just finished convection with finite volumes, and of course we learned about convection with finite differences as well. Right? When you compare convection to diffusion, convection is it's not that it's more difficult, but a lot more issues can arise when you try to solve convection. Okay. Okay. Because there are a lot of issues that cropped up with convection that we didn't have to deal with diffusion. Okay. All right. So let me just name a couple. Okay. And so the first one obviously is the issue with stability. Okay. And so if you're not careful with the grid spacing with your central difference scheme, you could have an unstable solution. And of course, that's very undesirable. Okay. Another issue, and we didn't really talk too much about this. We kind of touched on it a bit when we did convection with finite differences, but it's this issue of cross-stream diffusion. Okay. question. So would this be when the second window opens up on the project? You would actually, so you would never do both at the same time. And so, you can, part one of the project is you kind of solve it using the normal methods with simple central difference. And then part two is you kind of do the same project with, with the higher order scheme. And so the way I kind of structure the code, or the way I would kind of prefer, is that you can kind of toggle it. And so you can have, if you comment out a certain portion of the code, you would run with the normal, with a normal way. And if you uncomment a certain part, then you would run with the higher order scheme, but you would never run both at the same time. Yeah, so this is think of this as kind of an improvement over the schemes that we've done before, not necessarily something different. Okay? And so you would never run both at the same time. Enhancement, yes, you can think like that. And so we had this kind of cross-stream diffusion thing that went on, right? So we only talked about it briefly, but remember, in 2D, we naturally have grids that kind of line up with the X and Y axes, right? And so you have something that looks like this, okay? But if your convection velocity doesn't match up with the grid, okay? And so, in other words, it goes something like this, right? And so if your convection velocities kind of form, at weird angles compared to the grid, what can happen is that your solution can have artificially increased diffusion. Okay. Okay. And this is also bad because when you set the diffusion, you want it to be just the diffusion. And so if you're having issues where your diffusion is being artificially increased, that's not a good thing. Okay. And this is especially an issue when you have unsteady situations where the velocity is changing directions with time. And so for certain time steps, you might have a certain amount of artificial diffusion, but then other time steps you might have a completely different number. Okay. And so if you have a static problem, where the convection velocity only goes in one direction, you can account for it. And so you can basically, reduce your regular viscosity, or excuse me, you can reduce your regular diffusion by the artificial amount, and you can get the real one. But if your solution is kind of changing with time, that becomes a lot more difficult. Okay. And so these are pretty common issues with diffusion, and it's kind of why CFD is such an advanced field and such a strong interest field, because whenever you have a flow situation with convection, it becomes very difficult to model. Okay. And and so usually in an engineering situation when you have issues like this, you want to know what tools that you have available to you to address these issues. Okay. And so far, we haven't really introduced that many tools, right? And so in terms of tools, we kind of have two, right? And so we basically have two ways to that we can handle any kind of convection phenomenon. And so the first is to use a, and I'm going to use terminology with finite differences just because it's a bit easier to use. Okay, but the same kind of logic applies to finite volumes as well. And so the first tool that we use is a central differencing scheme. Okay. And the nice thing about central differencing is that this gives us second order accuracy. Which is a good thing, right? So second order accurate, that's usually a good goal to strive for. Okay. Our other tool to mostly deal with the stability issue is an upwinding scheme. Okay, so upwinding gives you a stable solution at the cost of accuracy, and so it's upwinding is only first order accurate. Okay. Right, so right now we have two ways to handle convection. Okay. And these are the two. And so, you know, I introduced these two at first because I think it gives a nice trade-off. And so you kind of have two options and they're both good at something. And so usually when you have kind of two options and they have their own defined roles, it's a little bit easier to pick up, especially the first time that you're doing stuff. Okay. But these are not the only options that we have, and actually far from it. Okay? And so there are different schemes that can, you know, first of all, give us a higher order of accuracy, and they can help us get around the stability problem as well. Okay. And in fact, you know, these are pretty widely known. And so I'm going to go ahead and switch back to my computer for a second. Okay. I'll come back to the iPad in a second, you know, but I just want to show you something really quick. All right, and so you open up a browser. Let's go to the place where all knowledge is born. We're going to go to Wikipedia. Okay. 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 And we're going to go to a page called Finite Difference Coefficients. Okay. Okay, so, you know, and this is kind of a nice moment too, just to show you that I'm not, you know, all the stuff we've been learning in this class, I'm not just pulling out of my ass, and so it's actually real stuff. Okay. And so let's go ahead and see, right? And so finite differences is it goes way beyond what we've learned in this class. And so there's a lot more finite difference schemes that are out there. Okay. But let me show you a couple that we've seen. And so let's look at this one first, right? So this is a finite difference scheme for a first order derivative. Okay. And let's look at the scheme with an order of accuracy of 2. Okay. Yeah. Okay. And so let's look at the scheme with an order of accuracy of 2, right? And so you can see here that for the -1 term, and so that's the left neighbor, then we have a coefficient of -1/2. Okay. For the 0th cell, and so that's the central node, you have a coefficient of 0. And then for the cell that's immediately to the right, we have a coefficient of 1/2. Okay. Let me remind you what our central difference scheme is. And so if you have d phi dx, okay, the way that we discretize this is we have phi I plus 1 minus phi I minus 1 divided by 2 delta x. Okay. Wireless mouse is better. Delta x. Okay. And so if we ignore the delta x for a second, okay, let's look at the coefficients for these terms. And so we have for phi I plus 1, we have a 1/2, right? 1/2. And then for phi I minus 1, we have a -1/2. Okay. And so this central difference scheme that we've been using all along, you know, is an actually real finite difference scheme, right? And so this is kind of what everyone uses for that. Okay. But what you'll see in this table is that there's a lot more options that are available. And so we can have a scheme that's 4th order accurate. Okay. We have a scheme that's 6th order accurate, and even an 8th order accurate scheme. And that one's pretty gnarly right there. And you can have different finite difference approximations for the different derivatives as well. And so for a 2nd order derivative, here is our usual scheme. And so we have a 1 minus 2, 1. And so that's our diffusion derivative. And you could go higher accuracy for this as well. And so you can do a 4th order scheme, 6th order, 8th order, and so on and so forth, right? And you can even go all the way up to a 6th order derivative, which is really gnarly. That's pretty crazy right there. Okay. And then you can scroll down and you can see coefficients for other schemes as well, right? And so this is all for central differencing schemes, but you can look at different forward differencing schemes as well. So this is a 1st order accurate one. Here's a 2nd order accurate, 3rd order accurate, so on and so forth. Okay. You could do the same thing for backward difference as well. Okay. And so this site is pretty fun, and so you kind of see all that's out there.
But the point I want to make is that, finite difference, there's a lot more options out there. And we can even have schemes that are higher accuracy. And usually the higher accuracy that you go, it fixes a lot of the issues that you've had before. Okay. Okay, and so what we can say that there are other schemes available. And in fact, many of those other schemes have better accuracy. Okay. All right. So for this, and so there's a lot out there, but for this particular class, I'm just going to focus on one for the finite difference. Okay. And so we're going to focus on the fourth order central difference scheme. Okay. And so this is for a first order derivative, of course. And so we have d phi. That's not what I want. d phi dx. Okay. This is equal to minus bi plus 2 plus 8 bi plus 1 minus 8 vi minus 1 plus vi minus 2, all divided by 12 delta x. Okay. Okay. And so since this is a representation of a first order derivative, we can use this to discretize our convection term. Okay. Okay. And if we do that, then our solution is going to be a lot more accurate, at least in terms of the convection. Okay. And what you'll see is that, a lot of the issues that we had before, particularly the second one, right? The first, even if you use the highest order accurate scheme, the stability problem doesn't go away completely, but it does make it better. Okay. And so it does give you a little bit more leeway to do for stability. Okay. So all that sounds great, right? And so, we switch the scheme and we fix all our problems, right? And so, that sounds great. So why haven't we been using this before? So there's a term, and so if you go deeper, and it's not unique to this, but in computational engineering, people who write codes that model physics for a living, there's a saying that everyone knows, and that there's no such thing as free lunch. Okay. And so all this seems great, right? And so we get a lot of benefits from doing this, but look at what we have to do in order to get those benefits, right? Normally, when we do a central differencing scheme, we only have to worry about two neighbors, okay? Right? So those are usually the only two that we have to do. If we want to implement this higher order scheme, we have to do a lot more work, right? In fact, we have to do twice as much work. And so we have to include more neighbors. Okay? And so, of course, more neighbors means that your equations are going to get longer. It's going to take longer to write. You have to account for them in your code, and so you have to, write longer codes. Okay. There's also logistical challenges associated with that as well. Okay. And so if you look at this equation, implicitly what it's assuming is that you have two neighbors to the left and two neighbors to the right. Okay. What if we have a situation that looks like this? Right. So here is our finite difference line. So we're just doing a 1D example for right now. Okay. And so if you apply that finite difference scheme to this node right here, okay, you'd have no problems here because you have two neighbors to the left, two neighbors to the right. Okay? So smiley face. But what if you try to apply that same scheme to this cell right here, okay, or to this node? Right, so the answer is no, right? Because we only have one neighbor to the right, and so even though we have two neighbors to the left, we only have one neighbor to the right, and so that makes this scheme invalid. And so logistically, there's a lot more challenges that you have to go over, and so that's what kind of makes the coding a bit more challenging. Okay? But we'll go over that next time because we're just about out of time today. And so, are there any questions on this before we wrap it up for today?
Yeah, I guess with that, for that particular problem, that second order accuracy is good enough.
Yes, well, and so what you can do is you can have different schemes. And so for all of these ones, or actually, I guess for these two, you can apply the fourth order scheme because you have enough neighbors. And then what you'll see is that you're going to need to write your code so that, when you have a situation where you can't apply the fourth order scheme, then you would apply a second order scheme to that one. Yeah, and so that makes the code a little bit more complicated to have to handle those situations too, especially in 2D. It gets a little bit messy there.
So what would you call your work then? Like a mixture of accuracies?
I would still go ahead and call it a fourth order accurate because normally you would use a lot more nodes than this, and so you'd probably have like 98-99% of your nodes using fourth order accurate. Maybe there's some fringe cases which are only second order, but usually that doesn't have too much of an impact on your solution. Yep. Mm-hmm. Yep.
So this would be used just at nodes, right?
Yeah.
Because the cell centers were different.
So for the finite volumes, we have a different scheme. We have a different method for that as well, and so we'll go over that on Wednesday. But yeah, finite volumes has their own version. Of this too. Okay. All right. Any final questions? All right. Thank you guys for tuning in today. On Wednesday, we'll continue this stuff, and then, we'll move on from there. Okay, so have a great evening, everyone, and I'll see you all on Wednesday.
Thanks, Dr. Chan.
Thanks, guys.
Thanks again, Dr. Tran.
Thank you, too.
One more time. Midterm 2, is that just all 2D with 2D for finite volumes?
So midterm 2 is going to be all the unsteady stuff, and so all the explicit Euler, implicit Euler, and then also the 2D diffusion with finite volumes. Yeah, so none of the convection stuff, but diffusion you should know. Yeah. Yep.
Megapascals, is it newtons over millimeters squared, or is it kilonewtons over millimeters squared?
I usually do meganewtons over meter squared, but I think newtons over millimeter square gives you the same thing too. Yeah.
Newtons over